Precalc chapter 8, section 7, last one of the chapter. So this is all about probability. We're going to use a lot of the counting from yesterday within this section. And so there's different kinds of probability we'll talk about. Probabilities, if it's mutually exclusive, independent, dependent, complement, and then basic probability as well. So some definitions we got to make sure we understand first is here the experiment is just when your happenings are uncertain. Whatever the result, the happenings or the result is uncertain. The outcomes are the possible results for an experiment, what might occur from your experiment. And then the sample space is the set of all possible outcomes, and so you're going to be able to count the actual sample space. This you need to count. And so when we count this, we may need to use the NPR, NCR to count our possible outcomes. And then the event is a subset you want. What do you want to occur? So the probability of the event E has N of E outcomes. So N of E is the number of outcomes you would want. The sample space is the N of S. N of S is the number of possible ways it could occur. And then the probability is found by dividing these. So P of E is a probability is found by dividing N of E over N of S. So it's what you want to happen divided by what could happen. That's kind of another way of thinking of it in very generic terms. If you had a review that had 20 questions on the review and you know 17 of them, what's the probability you'll answer 10 questions on the test correctly if, like your professor said, he's going to choose 10 from the 20 on the test. So if you know that of these 20 questions, 10 of them are going to be on the test, and you're able to study and know 17 of them, what's the probability you get all 10 right? So again, what do you want and what could happen? Two different things we need to count first. What do you want? You want 10 questions on the test, the 10 on the test. You want to be from the 17 you know, because if you want to get them all right, you don't care which of the 17, you just want 10 from the 17 you know. What could happen is that the 10 that are on the test could come from any of the 20 on the review. So probability of this occurring is going to be what we want. So we're going to choose 10 from the 17. So 17 C10. So here's an example where you can use your combinations to count this. You don't care which of this 10 from the 17, so it'll be 17C10. And then what could happen is 20C10. And so you would divide those. If you divide them, you get 0.1053, which is 10.53%. So don't do the rounding necessarily. A lot of people round the tenth and the decimal, then they have a more rounded percent. So if you keep it to 4 places here, when you create the percent, then you're still to 2 decimal places. So it's pretty precise there. So 10.53% chance. So mutually exclusive. What this is saying is that no overlap between events. So if two things are mutually exclusive, it's when these circles do not overlap. So mutually exclusive would be an example here with these two Venn diagrams. So if I look at the set of like odd numbers and the set of even numbers, there's no overlap. You look at like 1 and 3 and 5, they're over here, but then 2, 4, 6 are over here. There's no overlap. These are mutually exclusive. If they're non-mutually exclusive, then there is going to be an overlap. This area right here is called the intersection, and the intersection uses this symbol. All values in both sets would be called the union, which uses this symbol. And so if we look at cards, and if we call it the king in this set, and then we look at here, call it spades. So then this circle has all the spades, and then the other circle has all the kings. So like you have a king of diamonds. You have a king of hearts. you have a king of clubs, and then you have the king of spades, which actually has to go here because it's got, so king of spades has got to go here because it's in both. It's in the king's circle and the spade circle. So that would be the intersection of the two sets. So the union of two events would use this notation. So the probability of A union B. So you're looking at both A and B, and you don't care which set they come from. You want like one or the other. So probability of A, probability of B minus probability of A intersect B. The key word here in a lot of our statements is the word or. The word or means to add. And so whenever you see that word or can place the word or when you're in your logic, you should be thinking about adding the two probabilities together. You don't care which one that occurs. If they're mutually exclusive, there's no overlap, then you're just adding the two probabilities. You don't need to subtract the intersection. So example of that would be if it's a face card or a heart. So we still have to do probability of the different events. So probability of a face card or a heart. So to find that, we need to find the probability of a face card plus the probability of a heart minus the probability of the intersection of face card and heart. And so the probability of face card, to find that, how many face cards are there? If you're not aware with cards, we have the 1 through 10, and then you have the jack, queen, king, and then you have the ace. Those are different kinds of cards. You have 4 of each kinds of cards, are each different value. So these 3 are going to be the face cards, and of each one there's 4 different kinds of jacks and queens and kings. So then 4 times 3, that's 12 total face cards. So 12 out of, there's 52 cards in a deck. And if you're not aware of the number of cards, the number of face cards, you're always welcome to ask me, and I'll help you out with that. So plus the number of hearts, there are 13 hearts because there's 13 different kinds of cards. The ace is actually the 1. And then divided by 52. Now we have to subtract the overlap, the repeat. The reason why is when we count these 12 face cards, we counted 3 of them to be that are also hearts. We counted 3 of them twice because we counted them 3 of these: the king of hearts, the queen of hearts, and the jack of hearts. We counted them when we talk about face cards and the hearts. We counted them twice. So we need to subtract those 3 cards that we've counted twice, so we only really count them once. So this, if we added that together, would be 22/52, which if I reduce that, would be 11/26. And we could change it into percent. And some teachers, I'm okay with that. So you get 42.3%. I like percents just because we are able to compare them between other probabilities. I know some teachers prefer the fractions because then it's more precise and it's an exact value, which I understand that. I prefer the percents just so you can compare the different probabilities because that's what they're usually used for. So independent dependent is a different kind of probability. It's one where you're trying to find the probability of A and B. So that's the big difference here is and. You want more than one thing to occur. So the independent probability here is when the effects of one has no effect on the other. And then the dependent is when event A will change the experiment for event B. And then the math in it is really no difference. To find the probability of A and B, you take the probability of whatever event A is, and then you're going to multiply it by the probability of event B. The difference is when you're doing a dependent probability that the probability for B is going to change. You're assuming that A has occurred, so then the probability for B would be different. So we're looking at an independent example here. If we look at this bag of 10 marbles, independent would be using the word with replacement. That's typically a word that's used for these problems. Because if I want to find the probability of choosing a green and another green when I'm choosing marbles with replacement. So the probability of both those things occurring would be the probability of choosing a green one times the probability of choosing a green one, where the probability has not changed. So the probability of choosing green is 4/10 or 2/5 times 4/10 or 2/5 because I put that marble back. So I draw that marble out, I find out it's green, I put it back in, then I draw it out again and get 4/5 again. So using the reduced 2/5 and 2/5, you get 4/25 would be the fraction. Now if I did that same problem again, but let's look at it for dependent, it's the probability of green and green without replacement. So when I find these two probabilities, they're going to change. The probability of the first green one is the 2/5, the 4/10 or 2/5 times the probability of the second one. This first one I'm keeping in my hand, so now I only have 3 marbles left over, or 3 green marbles, and I only have 9 actual marbles in the bag, because this first marble is taking my options away. So if I multiply that, I'm getting 6/45. And so here's a good example where which of these probabilities is going to be better, and it's a little harder to see. I mean, most you can figure it out, but you may prefer the decimal form of those. So we get 16% and 13⅓%. So it's easier in the percentiles to compare the two probabilities. But for here, dependent, independent, they both are ands. The difference is that the dependent one, you need to change the probability of your second event. But the and is always going to be multiplying the probability. So or is adding, and is multiplying. Complement. The complement is the probability of the event not occurring. Not occurring. So we use the symbol here, this prime symbol. The probability of A prime means 1 minus the probability of A. So 100% minus the percent of probability of A, which is the probability of not occurring. So if you look at, so you're flipping coins, to get a head, it's 50%. The probability, the complement would still be 50%, not getting heads. If I'm choosing a letter from the alphabet, 1/26 is my probability of choosing a letter. The complement is going to be 25/26, the probability of it not occurring. So we use that in some of these problems to make it easier. So you make a sale, example here, you make a sale 1/3 of the calls. You call 5 people, what's the probability you make a sale? Now, to help me out, I can change that wording. You make a sale. I could say you make at least 1 sale. When we start using the words at least, at most, it tells me that I might use the complement. Not always, but it tells me complement might be a faster method of evaluating the problem. So for here, the probability of, I have 5 different phone calls. 1, 2, 3, 4, 5. Probability of making at least 1 sale is kind of tough. But what's not tough is the complement. So what is the complement of making at least 1? So what's the probability? We want the probability of making at least 1 sale. The complement to that would be making no sale. So that is not too hard to find. The reason why is because I know the probability of not making a sale for each phone call, and they're all going to be the same. If I want to try to find the probability of at least 1, I have a lot of different options. I could have the first phone call be the sale and then the others not, or I could have the second one be the phone call and the third one be a sale and the other one's not. So I have a lot of different options there, which makes it confusing. But if I say no sales, I only have one option. Every one of the events has to be 2/3 because that's the probability of me not making a sale. This is not making a sale. So 2/3, 2/3, 2/3, 2/3, 2/3. If I multiply them, because it's and, I want all of those to occur. This is the probability, if I multiply it together, of me not making a sale at all. I don't want that. I want at least 1 sale, so I want the complement of that, so 1 minus that. So the complement will help us sometimes when we're using the words at least or at most. So 1 minus, when you find the complement, you get 211 over 243, which is 86.83% chance that in 5 phone calls, I would make at least 1 sale. So I'm going to call that good for your probability, and we'll see you tomorrow.